A very good morning to you all. Introduction to Geochemistry, Lecture 2. Coming to the contents or outline of the topic, it includes the composition of planets, cosmic abundance of elements, Ardo-Hawkins rule, meteorites, and the classification of meteorites. Coming to the composition of the planets. Planets in our solar system are generally classified into two main types based on their composition. So these are the terrestrial planets and the giant planets. All the planets orbit the Sun in the same direction and in almost the same plane, and most of the planets have nearly circular orbits. And the average density of any substance it depends on in part on its composition. The terrestrial planets like Mercury, Venus, Earth, and Mars are primarily composed of rock and metal. Giant planets, including Jupiter, Saturn, Uranus, and Neptune, these are largely made of hydrogen and helium. So these are also known as gas giants, or these are a combination of ice, rock, hydrogen, and helium. That's why these are known as ice giants. Coming to the difference between the terrestrial planets and the Jovian planets. The terrestrial planets, these are the four inner planets, and these are Mercury, Venus, Earth, and Mars. And these are relatively small with diameters of 5,000 to 13,000 kilometers. And they have high average densities of around 4,000 to 5,500 kg per meter cube. And these terrestrial planets are mainly composed of rocky materials. Coming to the Jovian planets, the four giant outer planets are called Jovian planets. So these includes Jupiter, Saturn, Uranus, and Neptune. And these Jovian planets, they have large diameters of around 50,000 to 1,43,000 kilometers. And these will have low average densities of around 700 to 1700 kg per meter. And these composed primarily of hydrogen and helium. Coming to the first planet, that is known as a Mercury. Mercury is a solid and it is covered with the craters. And Mercury has almost no atmosphere. Mercury, it is formed approximately 4.5 billion years ago. And there are many competing hypotheses about Mercury's origin and development, some of which incorporate collision with the planetesimals and rock vaporization. As of the early 2020s, many broad details of Mercury's geological history are still under investigation, or they are in the pending data from space probes. Its mantle is mainly homogeneous, and Mercury is the eighth largest planet, and this is the first planet from the Sun. And Mercury, it is a rocky planet with a trace atmosphere. So its mantle is mainly homogeneous, which suggests that Mercury had a magma ocean early in its history, like the Moon. And according to current models, Mercury may have a solid silicate crust and a mantle overlying a solid outer core, a deeper liquid core layer, and a solid inner core. So Mercury is, while it is the smallest and the least massive planet of the solar system, its surface gravity is slightly higher than that of the Mars. And it is one of the four terrestrial planets in the solar system, which means it is a rock body like the Earth. And it is the smallest planet in the solar system with an equatorial radius of about 2,439.7 kilometers. Mercury's surface gravity is slightly higher than that of the Mars. And Mercury consists of approximately 70% metallic and 30% silicate materials. The surface of the Mercury, it is similar to the Earth's moon, which is heavily cratered. Its largest crater, Caloris Plantia, it has a diameter of 1,550 kilometers, which is about 1/3 of the diameter of the planet. Mercury is a classical planet that has been observed throughout the history and recognized as a planet or a wandering star. So in English, it is named after the ancient Roman god Mercurius. It is also known as a Mercury, god of commerce and communication, as the messenger of the gods. While it is the smallest and least massive planet of the solar system, its surface gravity is slightly higher than that of the Mars. And it appears to have a solid silicate crust and mantle overlying a solid metallic outer core layer and a deeper liquid core layer and a solid inner core. And the planet's density, that means Mercury has a density and it has the highest density in the solar system. It is the second highest in the solar system. This is around 5.427 grams per cc, and it's only slightly less than the Earth's density as 5.51 grams per cc. And Mercury core, it has a higher iron core content than that of the any other planet in the solar system. The most widely accepted theory is that Mercury originally had a metal silicate ratio, which is similar to common chondrite meteorites. So these are a type of the meteorites that I will discuss in the meteorites section. And this is Mercury is one of the 4 terrestrial planets in the solar system, which means it has a rocky body like the Earth. It's the smallest planet in the solar system with an equatorial radius of about 2439.7 kilometers. And coming to the Mariner's 10 observations, according to the Mariner 10 observations, Mercury has a thin atmosphere and it has a surface-based exosphere that spacecraft detected hydrogen and helium ultraviolet spectroscopy. The presence of sodium, potassium, and calcium, which are derived from the surface materials, they removed via one or more processes known as a sputtering. And hydrogen and helium, these are most likely originate from the solar wind. Mercury's surface has a similar appearance to that of the moon, showing extensive mare-like plains and heavy cratering, which indicating that it has been geologically inactive for billions of years. It is more heterogeneous than the surface of the Mars or the moon, both of which contain significant stretches of similar geology, such as maria or plateaus. This is a Mercury to scale, the picture showing the Mercury to scale among the inner solar system planetary mass objects. Coming to the Venus. Venus is the 6th largest planet and it is about the 3/4 the size of the Earth. And this has a surface which is rocky and very hot. The atmosphere of the Venus, it completely hides the surface and traps the heat. And Venus is made up of a central iron core and a rocky mantle, which is similar to the composition of the Earth. Its atmosphere, it is mainly consists of carbon dioxide, it's roughly around 96%, and nitrogen 3%, with small amounts of other gases. Venus is the second planet from the Sun. It's often called the Earth's twin or sister planet for having almost the same size and the mass and the closest orbit to the Earth. While both the rocky planets, Venus has an atmosphere much thicker and denser than the Earth and any other rocky body in the solar system. Its atmosphere, it is mainly composed of carbon dioxide with a global sulfuric acid cloud cover and no liquid water. At the mean surface level, the atmosphere reaches a temperature of 737 Kelvin and a pressure 92 times greater than Earth at sea level, turning the lowest layer of the atmosphere into a supercritical fluid. Venus has a weak magnetosphere, lacking an internal dynamo. It is induced by the solar wind and the atmosphere interacting. Venus has a core, a mantle, and a crust, and Venus has a dense atmosphere composed of 96.5% of carbon dioxide, 3.5% of nitrogen, but both exist as supercritical fluids at the planet's surface with a density 6.5 that of the water, and traces of other gases, including sulfur dioxide, are also seen in the surface of the Venus. The similarity in size and density between the Venus and the Earth, it suggests that they share a similar internal structure like a core, a mantle, and a crust. And the core is partially liquid. And the slightly smaller size of the Venus, it means pressures are 24% lower in the deep interior than the Earth's surface. So there are almost 1,000 impact craters on Venus can be seen, and these are evenly distributed across its surface. So that means volcanic activity can be seen on the surface of the Venus. Coming to the Earth, Earth is the fifth largest planet and the third from the Sun. And liquid, it covers most of the, that means about 71% of the Earth's surface. Earth has one moon. In the next lecture, we will be discussing about the interior structure of the Earth in detail. Coming to the albedo features. What are albedo features? So actually, there is no topography that is visible on Mars from the Earth. And albedo features are nothing but the bright areas and dark margins which can be seen through a telescope are known as the albedo features. And the bright red ochre areas, so these are nothing but the locations where fine dust it covers the surface. There are bright areas which includes Hellas, Tarsis and Arabia Terra. And the dark gray markings, they represent the areas that the wind has swept clean of the dust and it has cleared all the dust and leaving behind the lower layer of the dark and rocky material. And these dark markings which are visible, and these are most distinct in a broad belt from 0 degrees to 40 degrees south latitudes. And the polar ice caps, these are well-known telescopic features of Mars. Coming to the volcanic features. Volcanic structures and landforms, they cover large parts of the Martian surface. The most conspicuous volcanoes on Mars are located in the Tarsis and Elysium. And Mars has the greatest diversity of impact craters types of any planet in the solar system. Geologists think one of the reasons volcanoes on the Mars were able to grow so large is that Mars has fewer tectonic boundaries in comparison to the Earth. Lava from a stationary hotspot was able to accumulate at one location on the surface for many hundreds of millions of years. Coming to the sediments on the surface of the Mars, flowing water, it appears to have been common on the surface of the Mars at various points in its history and especially on ancient Mars. Many of these flows, they carved the surface, forming valley networks and producing sediments. And the sediment has been redeposited in a wide variety of wet environments, including alluvial fans, meandering channels, deltas, lakes, and perhaps even oceans. The process of deposition and transportation are associated with gravity. Due to gravity-related differences in water fluxes and flow speeds, inferred from grain size distribution, Martian landscapes were created by different environmental conditions. A wide variety of other sedimentological features these are present locally on the Mars, including glacial deposits, hard springs, dry mass movement deposits, especially landslides, and cryogenic and periglacial materials, etc. And it has a wide variety of sedimentary minerals, including clays, sulfates, and hematite. Groundwater has been implicated in the cementation of aeolian sediments, and we can see the formation of sedimentary minerals. These are the interesting geomorphological features like avalanches, possible caves, inverted relief. All these are the features which can seen on the surface of the Mars. And the evidence of avalanche included dust clouds rising from the cliff. And these geological events are theorized to be the cause of the geological patterns known as the slope streaks. And NASA scientists studying pictures from the Odyssey spacecraft have spotted what might have seen 7 caves on the flanks of the Arsia Mons volcano on the Mars. Some areas of the Mars, they have shown inverted relief features, and where the features that were once depressions like streams are now above the surface. It is believed that materials like large rocks were deposited in low-lying areas. Later, wind erosion has removed much of the surface layers but left behind the more resistant deposits. Coming to the groundwater, Researchers hypothesize based on the geological surface features of Mars and the results of numerical simulations that the several prominent features on the planet have been produced by the action of groundwater, and that the Mars may have had a planet-wide groundwater system. According to the theory, groundwater with the dissolved minerals came to the surface in and later around the craters and helped to form layers by layers, adding minerals, especially sulfates and other cementing sediments. Coming to the Jupiter. Jupiter is the fifth planet from the Sun and the largest in the solar system. It is a gas giant with a mass more than 2.5 times that of the all other planets in the solar system. And Jupiter's primary composition, it is hydrogen and helium, mirroring the Sun's makeup. The planet's atmosphere also contains trace amounts of other gases like methane, ammonia, and water. These are formed from abundant elements combining with hydrogen under high pressure, high temperature conditions. These trace gases are also found in the interior where they exist in a supercritical state. So that's why you can see 76% hydrogen, 24% helium, methane, ammonia and water, and trace elements, and deuterium. And also Jupiter's helium abundance is 80% of the Sun, which is similar to the Saturn's composition. And the Jupiter is about 11 times wider than the Earth, whereas its mass is 318 times that of the Earth, and it is 2.5 times the mass of all the other planets in the solar system combined. And it is the largest planet in the solar system with a diameter of 1,42,984 kilometers at its equator. And Jupiter's volume, it is 1,321 times that of the Earth, and it has the strongest magnetic field, and it has a dipole moment of 4.17 gas. And Jupiter's magnetic field is the strongest in our solar system, which is generated by electrical currents within its metallic hydrogen core. It is significantly more powerful than the Earth's with a dipole moment of 20,000 times greater. And Jupiter's magnetic field, it creates a magnetosphere so large, it begins to avoid the solar wind almost 3 million kilometers before it reaches the Jupiter. And its average density is about 1.3 grams per cc, which is lower than those of the 4 terrestrial planets. Jupiter is massive because it has a large diameter. This is about 11 times that of the Earth, and its density is only 1.33 grams per cc, which is 1/4 of the Earth, and it's only slightly more than the 1 gram per cc characteristic of the water. And Jupiter, it has the, as we have discussed, it has the strongest gravity in our solar system. Coming to the moons of the Jupiter, at least 97 moons orbit the planet, and the 4 largest moons, Io, Europa, Ganymede, and Callisto, orbit within the magnetosphere, and these are visible with common binoculars. Ganymede is the largest of the 4, and it is larger than the planet Mercury. Jupiter is surrounded by a faint system of planetary rings, and it has 4 large Galilean moons and 12 smaller named moons, and 23 more recently discovered, but these are not named as moons. Coming to the Jupiter's red spot. Jupiter's red spot is a giant swirling anticyclone in the planet's atmosphere. It's a persistent high pressure storm that has been observed for over 150 years. And this is located 22 degrees south of the equator. It's large enough to engulf Earth multiple times, and it is a red-orange color. It's still a mystery to scientists. The Great Red Spot, it is larger than the Earth. The Great Red Spot is a huge storm of the swirling gas that has lasted for hundreds of years. And Jupiter does not have a solid surface. The planet is a ball of liquid surrounded by gas. Coming to the Saturn. Saturn is the second largest planet and the 6th from the Sun. and it is named after the Roman god of wealth and agriculture, who was the father of the god of the Jupiter. Saturn is made of materials which are very lighter than the water. Like Jupiter, Saturn, it is made mostly of hydrogen and helium. Saturn's center, it consists of a dense core metal. This is consists of iron and nickel, which is surrounded by rocky material and other components or compounds which are solidified by intense pressure and heat. And Saturn is enveloped by liquid metallic hydrogen inside a layer of liquid hydrogen, similar to Jupiter's core, but it is considerably very small. Saturn is composed mainly of hydrogen and helium. So that's why this is also known as a gas giant. And it doesn't have a true surface, though it's similar to the Earth, like it have a solid core. And this planet is mostly made up of swirling gases and liquids, which are deeper down. And this Saturn, it is of different colors. This is in many different shades of yellow, brown, and gray. And this is blanketed with the clouds that appear as a faint stripes, jet streams, and storms. And Saturn orbits the Sun at a distance of around 9.59 Armstrong units, which is roughly equal to 1,434 million kilometers, with an orbital period of around roughly 30 or 29.45 years. Saturn, it consists of a hexagonal wave pattern around the north polar vortex in the atmosphere. This is about 78 degrees north, and it was first noted in Voyager images. And the planet's rotation makes it an oblate spheroid, means a ball flattened at the poles, and it is bulging at the equator. And its equatorial radius is more than 10% larger than the polar radius. And it has a hot interior, that means reaching 11,700 degrees centigrade at its core, and it radiates 2.5 times more energy to space than it receives from the sun. And Saturn has an intrinsic magnetic field. It has a simple symmetric in shape, that is known as a magnetic dipole, and its strength at the equator is around, that is magnetic strength at the equator is around 0.2 gas. And Saturn's magnetic field is smaller than the Jupiter's, but still it is 578 times as powerful as Earth. Coming to the Saturn rings. Saturn rings are thought to be pieces of comets, asteroids, or shattered moons that broke up before they reached the planet, or torn apart by Saturn's powerful gravity. The rings are very thin, though they are 250,000 kilometers or more in the diameter. They are less than 1 kilometer thickness. Saturn's rings are made of billions of small chunks of ice and rock coated with other materials such as dust. The ring particles they mostly range from tiny dust-sized icy grains to chunks as big as a house, and a few particles are as large as mountains. The rings would look mostly white if you look at them from the cloud of or from the tops of the Saturn. And interestingly, each ring orbits at a different speed around the planet. Saturn's ring system extends up to 282,000 kilometers from the planet. Yet, the vertical height is typically around 30 feet or 10 meters in the main rings. Coming to the Uranus. Uranus is the third largest planet and the seventh from the Sun. Uranus is one of the giant gas planets, and it is bluish green in color because of the methane in its atmosphere. And Uranus is the seventh planet from the Sun, and most of the planet it is made of water, ammonia, and methane in a supercritical phase of matter, which astronomy calls it as ice or volatiles. The planet's atmosphere, it has a complex layered cloud. It has a cloud-like structure and has the lowest minimum temperature. This is about 49 Kelvin of all the solar system's planets. Coming to the axial tilt, its axial tilt of Uranus is 82.23 degrees with a retrograde rotation period of 17 hours and 14 minutes. Retrograde rotation means it has a marked axial tilt of 82.23 with a retrograde rotation period of 17 hours and 14 minutes. This means that an 84 Earth year orbital period around the Sun, its poles get around 42 years of continuous sunlight followed by 42 years of continuous darkness. This is the retrograde rotation. Coming to the internal structure, Uranus' mass is roughly 14.5 times that of the Earth, making it the least massive of the giant planets. Its diameter is slightly larger than the Neptune's, and it is roughly 4 times that of the Earth. Uranus' mass is roughly 14.5 times, making it the least massive of the giant planets. A density of 1.27 grams per cc, it makes the Uranus the second least dense planet after the Saturn. And wind speeds, they can reach up to 560 miles per hour or roughly around 900 kilometers per hour on Uranus. Winds are retrograde at the equator, blowing in the reverse direction of the planet's rotation. The density of 1.27 grams per cc, this value indicates that it is made primarily of various ices such as water, ammonia, and methane. The total mass of the ice in Uranus interior is not precisely known because different figures emerge depending upon the model chosen, but it must be between 9.3 and 13.5 Earth masses. And hydrogen and helium, they constitute only a smaller part of the total, between 0.5 and 1.5 Earth masses. Coming to the moons of Uranus, like the other giant planets, Uranus has a ring system, magnetosphere, and many natural satellites. Uranus has 28 natural satellites or moon, while most of the satellites orbiting other planets take their names from Greek or Roman mythology. Uranus moons are unique in being named for characters from the works of William Shakespeare and Alexander Pope. All of Uranus' inner moon appears to be roughly half water and half rock. The composition of the other moons remains unknown, but they are likely captured asteroids. Neptune is the eighth and farthest known planet from the Sun. It is the fourth largest planet in the solar system by diameter. The third most massive planet and the densest giant planet. It is 17 times the mass of the Earth. Compared to Uranus, its neighboring ice giant, Neptune is slightly smaller but more massive and denser. Being composed primarily of liquids and gases, it has no well-defined solid surface. Neptune orbits the Sun once every 164.8 years at an orbital distance of 30 astronomical units, and it is named after the Roman god of the sea. Neptune does not have a solid surface, and its atmosphere is mostly made up of hydrogen, helium, and methane. Neptune's atmosphere is faintly blue in the optical spectrum, only slightly more saturated than the blue of the Uranus atmosphere. Neptune's internal structure resembles that of the Uranus, and Neptune's mass of 1.024 into 10 to the power of 26 kg, it is intermediate between the Earth and the larger gas giants. Pressure in the atmosphere, it reaches about 10 gigapascal or about 105 atmosphere or 10 to the power of 5 atmospheres. Coming to the Neptune's magnetosphere, this consists of a magnetic field that is strongly tilted relative to its rotational axis at 47 degrees centigrade and offset of at least 0.55 radius, which is roughly around 13,500 kilometers from the planet's physical center, resembling Uranus' magnetosphere. Neptune's weather, it is characterized by extremely dynamic storm systems with winds reaching speeds of almost 600 meters per second, exceeding supersonic flow. And Neptune's is more varied weather when compared to the Uranus. It is due in part to higher internal heating. Sometimes Neptune is even farther from the Sun than dwarf planet Pluto. Coming to the orbit and the rotation, one day on Neptune, it takes about 16 hours, the time it takes for Neptune to rotate or spin once. And Neptune makes a complete orbit around the Sun, that means a year in Neptunian time, in about 165 Earth years or 60,190 Earth days. The average distance between the Neptune and the Sun is about 4.5 billion kilometers, the mean distance from the Earth to the Sun, and it completes an orbit on average every 164.79 years, subject to a variability of around plus or minus 1.1 years. The perihelion distance is 29.81 Armstrong units, and the aphelion distance it is 30.33 Armstrong units. Neptune's orbital eccentricity, it is only 0.008678, making it the planet in the solar system with the second most circular orbit after the Venus. Coming to the Kuiper belt, the Neptune's orbit, it has a profound impact on the region directly beyond. This is known as the Kuiper belt. So this is a ring of small icy worlds similar to the asteroid belt, but far larger, extending from Neptune's orbit at 30 Armstrong units out to about 55 Armstrong units from the Sun. This Kuiper belt, it is very similar to the asteroid belt, which occurs between the Mars and Jupiter, but it is far larger, that is 20 times as wide and 20 to 200 times as massive. Like the asteroid belt, it consists of mainly of small bodies of remnants from which the solar system has formed. And Neptune has 16 moons, and Triton is the largest Neptunian moon. So this accounts for 99.5% of the mass in the orbit around the Neptune, and it is the only one massive enough to be the spheroidal in structure. Triton was discovered by William Lassell just 17 days after the discovery of the Neptune itself. And Triton is the only large moon in the solar system that circles its planet in a direction opposite to the planet's rotation. Starting near the planet and moving outward, the main rings are known as Gale, Leverrier, Lassell, Arago, and Adams. The rings are thought to be relatively young and short-lived. This is about the periodic table of elements. Coming to cosmic abundance of elements. The most abundant element in the universe, as it is well known that it is hydrogen. So this makes up about nearly 3/4 of all the matter. And helium, it makes up only about 25%. And oxygen is the third most abundant element in the universe. And all the other elements, they are relatively very rare. Coming to the earth as a whole, the composition, it consists of iron, it's roughly around 32%, and followed by oxygen, 30%, followed by silicon, 15%, magnesium, 13.9%, sulfur, 2.9%, nickel, 1.8%, calcium, 1.5%, and aluminum, 1.4%, and other elements, they constitute only 1.2%. The core of the earth is believed to be primarily composed of iron. This is around 88.8%, while smaller amounts of nickel around 5.8% and sulfur 4.5% and less than 1% of trace elements. Coming to the relative abundance of non-volatile elements in a decreasing order. Suppose if we take this is the abundance of non-volatile elements. Oxygen followed by silica, followed by aluminium, iron, calcium, sodium, potassium, and magnesium. This is about the relative abundance of non-volatile elements. Coming to the elementary abundance of meteorites in decreasing order, oxygen, followed by iron, followed by silica, magnesium, sulfur, nickel, aluminium, and calcium. Coming to the elementary abundances in sun in decreasing order, hydrogen, helium, oxygen, followed by iron, magnesium, nickel, silicon, and carbon. So what is the cosmic abundance of elements? What does it indicate? On the basis of the composition of meteorites, solar and stellar matter, Goldschmidt in 1937, he gave the cosmic abundance of elements. And the elemental abundances, they show rapid exponential decrease for elements of low atomic number. And this is followed by a constant value for the heavier elements. So that means there is an abundance of rapid exponential decrease for elements of the low atomic number, which is followed by an almost constant value for the heavier elements. And elements of even atomic number are more abundant than those of the odd atomic numbers on either side. So actually this was first suggested by Oddo in 1914 and Harkins in 1917. That's why this rule is popularly known as Oddo-Harkins rule. The relative abundances of elements of higher atomic number than nickel, they vary less than those of the elements of lower atomic number. Only 10 elements like hydrogen, helium, carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, and iron, they all with atomic number less than 27, they show appreciable abundance because these are very minerals with low atomic number. Of these, hydrogen and helium, they far outweigh the other 8. That means their abundance is much more when compared to the other elements like carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, and iron. There is a pronounced abundance peak at atomic number 26 and smaller peaks at several other heavier atomic numbers. The absolute, how we do explain the abundances of elements? The absolute abundances of the elements, they depend upon the nuclear materials rather than the chemical properties. And these are related to inherent stability of the nucleus. That means an element which is uniquely characterized by the number of the protons, these are also known as a Z in its nucleus, but the number of neutrons, these are associated with the protons, can vary. As a result, what will happen? An element will have several number of isotopes. They differ in mass number of atomic weight and stability, but not appreciable in chemical properties. So similarly, there are isobars, which are different elements with the same mass number and different values of N and Z, and these are known as isotones, which are different elements with the same neutron number, but with the different values of A and Z. Coming to the Oddo-Hawkins rule, even atomic numbered elements are more dominant than the adjacent odd number ones. For example, if you take oxygen, its atomic number is 8. This is more abundant than either nitrogen or any other element like fluorine. If you take calcium, this is more abundant than potassium or scandium. That means elements of even atomic number are more abundant than the odd. The exceptions to this rule are hydrogen and beryllium, iron, etc. The Oddo-Hawkins rule states that elements with even atomic number are generally more abundant than the universe and than their neighboring elements with odd atomic numbers. So, as we have discussed that carbon, the atomic number 6, it is more abundant than both boron and nitrogen. This pattern is observed across various cosmic abundance data. Coming to the hydrogen and helium dominance, hydrogen 75% by mass and helium 24% by mass. These are the most abundant elements formed during the Big Bang. Coming to the decreasing abundance with atomic number, as atomic number increases, elemental abundance generally decreases due to nucleosynthesis limitations in advanced burning cycles. Exceptions to the Oddo-Hawkins rule, elements like lithium, beryllium, and boron, they are the exceptions to the Oddo-Hawkins rule because they unusually have low abundances due to their destruction in the stellar interiors. This is because most of the universe lithium, beryllium, and boron, they are made by cosmic ray spallation, not ordinary stellar nucleosynthesis, and beryllium has only one stable isotope, causing it to lag in abundance with regard to its neighbors, each of which has two stable isotopes. Beryllium, which despite at an even atomic number is rarer than adjacent elements lithium and boron. Beryllium is even more rare than lithium and boron. Even though the primary source of all the three elements is cosmic ray spallation, scientists believe that beryllium does not follow the rule because it has only one stable isotope. Lithium and boron each have two stable isotopes. Hydrogen, atomic number 1, is an odd atomic number element, but the most abundant due to its primordial origin from the Big Bang. Iron, due to its nuclear stability, it is relatively more abundant among the heavier elements. So these are the certain exceptions. Coming to the meteorite. Meteorite is a piece of rock from outer space that strike the surface of the earth. So these are known as any extraterrestrial material which hit the surface of the earth. A meteorite is a meteorite before it hits the surface of the earth. Meteorites are extraterrestrial objects composed of a variety of materials. They are broadly classified as main categories like stony meteorites, iron meteorites, and stony iron meteorites. Stony meteorites, they are primarily rocks with iron and nickel, often making a small portion. Iron meteorites are largely metallic, composed of iron and nickel with trace amounts of other elements. Stony iron meteorites are mixtures of both rock and metal with a variety of compositions. These are also known as shooting stars. And the rate of the meteoritic fall, it is between 30,000 and 1,50,000 tons annually. So as they have classification like iron meteorites, and then stony meteorites, stony iron meteorites, and they may be consist of nickel iron alloy, and they consist of crystalline silicate like olivine or pyroxene, and they also consist of troilite iron sulfide mineral, a mixture of sedimentary or metamorphic rocks. So these are different meteorites which hit the earth. Coming to the meteor showers, many meteorites are seen during specific seasons of the year when the Earth's orbit passes through a belt with a high concentration of dust or cosmic dust and other particles. Passing through one of these belts each year in mid-August, it causes the Perseid shower, the Lenoid shower, which happens around in the middle of the November. So these are different meteorites which are hit in 1938, 1954, 1992. Like that, meteorite showers have been, or meteorite dust can be seen in several parts of the globe. In 1938, a small meteorite has crashed through the roof of a garage in Illinois. And in 1954, a 5 kg meteorite fell through the roof of a house in Alabama. Like that, you can see a number of meteorites which has hit the earth. Coming to the classification of the meteorite. Modern classification, it divides the meteorites into groups according to the structure, chemical composition, and mineralogy. Modern classification of meteorites, it is very complex. There are 4 meteorite types like that: aerolites, siderolites, and tektites. So coming to the detailed classification of the meteorites, these are divided into 4 sections. Number 1, stony meteorites. These are also known as aerolites or stones. Again, they are divided into chondrites and achondrites based on the presence of chondrules. Coming to the second category, stony iron meteorites. These are also known as siderolites. They consist of 50% metal and 50% silicates. Again, it includes 2 main types like pallasites and mesosiderite. Coming to the third category, iron meteorites. These are also known as siderites, average about 98% metal, and they again divided into hexahedrites, octahedrites, and ataxites. And coming to the fourth category, these are known as tektites. Coming to the first category, stony meteorites. These are also known as aerolites. They consist of 90% of silicate minerals and 10% iron nickel alloy. Stony meteorites, they can be classified as chondrites and achondrites. On the basis of texture, the aerolites are stones. They are again divided into chondrites and achondrites. So these are essentially rocks from space, often containing small grains of nickel and iron and sometimes other minerals. The chondrites are so named because of the presence of chondrules or chondri, which are small rounded bodies averaging around 1 millimeter in diameter. Mainly they consist of olivine or pyroxene. Coming to the chondrites classification, they consist of 40% olivine, 30% pyroxene, and 10% plagioclase, and 10% nickel iron alloy, and 2% native copper, and 2% copper, 2% chromite. The presence of condyles or chondri, which are small rounded bodies averaging around 1 millimeter in diameter, consisting of olivine or pyroxene, and these are similar in composition to the mantle and the crust of the earth. And chondrites are believed to be among the oldest rocks in the solar system. And carbonaceous chondrites, that is around hydrous iron magnesium silicate, and contain 10% complex organic compounds. Coming to the achondrites, so they consist of 80% pyroxene and plagioclase, 10% iron nickel alloy, 2% magnetite, and 2% chromite. And these chondrites, achondrites, they lack chondrules, and they resemble igneous rocks on the earth. And Murchison meteorite, they fell in Australia in 1969. It is of achondrite, and these are of non-biological origin for organic compound. Coming to the stony iron meteorite, these are also known as the siderolites. The siderolites are stony meteorites. They are made up of nickel, iron, and silicates in equal proportion. There are again two distinct groups like pallasites and mesosiderites. What are pallasites? Pallasites are continuous base of nickel iron enclosing grains of olivine, which often they show good crystal forms. Coming to the mesosiderites, so here the metal phase is discontinuous and the silicates are mainly plagioclase feldspar and pyroxene. Sometimes they contain accessory olivine as well. Coming to the iron meteorites, third category, this is also known as siderites. So one or two nickel metallic phases and accessory troilite, that is iron sulfide and graphite. And they also consist of dabrilite, FeCr2s4. Dabrilite is a rare sulfide mineral and it crystallizes in the cubic system and it typically forms black platy aggregates. The mineral is a member of the linite subgroup with the largest spinel supergroup, and it was named in honor of the Gabriel Auguste Dabry, a French mineralogist and geologist. And there are accessory minerals which are present in iron meteorites as a small rounded or lamellar grains scattered throughout the metal. And these siderites, they have a peculiar pattern. This is known as a Wittgenstein pattern. Metals generally show a definite structure. This is known as a Wittgenstein structure or Wittgenstein pattern. So this can be brought by etching the polished surface with alcoholic solution of nitric acid. This structure consists of a lamellae of camosite, a nickel iron alloy with 6% nickel, which is bordered by tennite. Tennite means it is a nickel iron alloy with about 30% nickel. So the Wittgenstein structure, it is distinctive. It is a lattice work-like pattern. This is found in certain iron meteorites and in some steels, which is formed due to slow cooling of iron nickel alloys. And it appears as intersecting bands of nickel iron phase. This pattern, which is a result of slow cooling and crystallization of these alloys deep within the planetary bodies, making it a key indicator of extraterrestrial origin for iron meteorites. And this structure is a typical of subsolidus exsolution, which is an alloy that has cooled very slowly from a high temperature. Subsolidus exsolution is a process where a single homogeneous solid solution mineral separates into two or more distinct mineral phases while remaining in the solid state, that means below the solidus temperature. This occurs due to changes in pressure or temperature that make the original solid solution unstable. The separated phase typically form intergrowths such as lamellae within the original mineral structure. Coming to the iron meteorites, so these are again divided into three types like hexahedrites, octahedrites, and ataxites. Hexahedrites are irons or iron meteorites consisting entirely of camosite, whereas octahedrites, here the lamellae are parallel to the octahedral planes, an originally homogeneous crystal of nickel, iron, and meteorites showing Widman structures are therefore known as octahedrites. Then what are ataxites? Ataxites are nothing but the iron nickel alloy, which is composed of chamosite and titanite. The concentration of nickel is about 14% and consists largely of olivine tennite. These are some of the pictures of iron meteorite. Tamintet iron meteorite. This is found in 1864 in Sahara. This is roughly weighs about 500 kg. And polished surface of meteorite glowing iron and nickel. You can see here. These are the references. Thank you for your time. See you in the next video.